The next talk will be given by Dr. Rees, and it will be entitled Current Status of SAR Arc Observations and Theory.
To give a status report on SAR Arcs in 10 minutes is a rather ambitious undertaking, and I'm not sure how successful I will be. But let me... Sorry. It is difficult to see these slides, isn't it? Well, I have a picture of it here. In any case, this first figure is nearly identical to the one that Dick Thorne had this morning, and it illustrates the region of the ionosphere and the magnetosphere relevant to SAR Arc formation. And you can, as you stare at these regions and read the various labels, let me just quickly qualitatively summarize what the, let's call it time history of a SAR Arc would be. And during a geomagnetic storm, the magnetosphere is compressed and the plasma pause moves inward to lower L values, and the magnetospheric ring current is then enhanced. Now, the source of SAR Arc energy appears to be the ring current interacting with the plasma pause electrons. The ring current proton energy is transferred to the ambient plasma through wave-particle interaction, heating the electron gas at the plasma pause. The energy is then transported by particle flux along geomagnetic field lines to the ionosphere, where the plasma density is high enough for the plasma to thermalize through Coulomb interactions. Energy is then conducted into the F region of the ionosphere in the form of heat in the electron gas. The SAR Arc region is characterized by a depression in the electron density and an enhancement of the electron temperature. The electron density depression is conducive to SAR Arc formation by allowing the high electron temperature to penetrate low to low altitudes where the atomic oxygen number density is high. The electrons in the high-energy tail of a Maxwellian distribution then excite the oxygen atoms to the singlet D level, but the fraction of electrons with energy sufficient to excite higher levels or ionize is too small in SAR Arcs, and therefore you do not get the sort of radiations associated with normal aurora. The O singlet D atoms then radiate in the characteristic 6300 angstrom emission at those altitudes where collisional deactivation is small, and this is at this 400 kilometer level. The SAR Arc will persist as long as high electron temperatures exist at 400 kilometers. And since the SAR Arc is a rather long-lived phenomenon, 10 hours or longer, it really represents a manifestation of the slow release of energy that occurs during the recovery phase of a geomagnetic storm. Now, this is the overall qualitative picture. Let's look at some parameters that are relevant to the formation of the SAR Arc. And here, I guess I don't have the figure of this, so I have to look and see what we have. The SAR Arcs occur from barely detectable intensities. This is the intensity in Rayleigh's emission rate, 10, 100, 1000. And here we give the energy deposition rate in ergs per centimeter squared per second. There are two curves shown. One applies to the, let's see, this would be a low electron density profile. This would be a high electron density profile. These two profiles pretty much span the range of observed electron density profiles in the topside ionosphere during SAR Arc occurrence. We can see that a 1 kilorayleigh SAR Arc requires an energy deposition rate of less than a tenth of an erg per centimeter squared per second, of the order of 0.05. And even the brightest arcs that have been observed are in this energy range. Now, the consequence of this energy deposition, and here we show three cases of SAR Arcs, one of emission rate 96 Rayleighs, 960, and this is 48 4 kiloreles, 4.8 kiloreles. The energy deposition is quite small, less, well, this is 0.12. And these are the temperature profiles that are associated with this energy deposition. Even for the very brightest arcs, we only need a temperature of some 8,000 degrees at 1,000 kilometers. I should add that these fluxes are fluxes that refer to fluxes that are heat fluxes coming down through the 1,000 kilometer level. And of course, the energy is absorbed as the heat comes down locally. Now, the next question is, what is the magnetospheric energy required? And again, if we look in this energy range that is required at 1,000 kilometers, and we pick 3 typical plasma densities at the plasma pause, we find that the mean energy, mean electron energy, is of the order of 3 to 5 or 6 eV. So this is then all that is required for the mean energy of electrons at the plasma pause. I have these figures here, and so I think I'll go to these instead of looking at the board. Now here, in this next figure, we take this mean electron energy, and under the assumption, which is more than an assumption, it appears that this is in fact what occurs. If this energy is due to the ion cyclotron waves absorbed by the electron plasma by Landau damping, then the fraction of energy that is absorbed is somewhere of the order of 3/10 to 5/10 of the total energy. The A pluses refer to the degree of anisotropy in the pitch angle distribution, and as we heard this morning, the figures appear to be of the order of unity for this anisotropy. Now, one consequence of this mechanism exciting the SAR Arc, at least depositing energy high in the magnetosphere, which is then transferred down into the ionosphere, is that the waves, these ion cyclotron waves, grow, but only over a very limited frequency range. This is following the theory of Cornwall and his collaborators. In this case, we have taken their latest work and plotted the growth rate for a typical situation of energetic proton densities of 5 per centimeter cubed, an anisotropy factor of 1.5, ion cyclotron frequency of 17.8, and beta is the ratio of particle energy density to magnetic field energy density. The n's, again, are 2 values for the ambient plasma density. So one test of this theory for the generation of SAR arcs is the presence of these waves over a rather limited spectrum. And as far as I know, and perhaps someone knows differently, this is a frequency range that has not been observed as yet from satellites.
What is the frequency range there? Can we raise the slide a bit?
I'm sorry, I have it on my figure here. I didn't realize it wasn't there. I can't see it here. It for this curve here, it is 9 hertz, and for this figure, it is 7. Here we are. The scale.
The other way.
1, 3, 5, 7, 9, 11, 13. So that this is the frequency range that is involved here. Yes, in hertz. The question came up the other day as to whether or not fluxes of suprathermal particles might be associated with SAR arcs. And I've gone through just some quick calculations. If the initial energy of electrons is 10 eV or less, all the energy is deposited above 1,000 kilometers, and energy is conducted downward into the ionosphere, then one would not see any difference between that mechanism and one of strict heat conduction. But when we get to higher energies of some 30, 40 eV, then this does make a difference. And first we need to know just what fraction of the energy is deposited in the electron gas and what fraction is deposited in the neutrals. And you can see that for very low electron energies, virtually all of the energy goes to the electron gas. But for, say, 40 eV electrons, only about 1/4 of the energy goes into the electron gas, and the rest goes into such things as exciting O single D and other things as well. So the criterion of significance of a particle flux playing a role in the generation of a SAR arc is if this energy is deposited at 400 kilometers, as if the particles actually can penetrate to 400 kilometers. And that is what is plotted here. This refers to the 400 kilometer altitude level. Now, taking these figures, we look at the number of photons, and this is on the blackboard now, the number of photons that are produced per incident unit electron flux. And I'll read the numbers off here. You can see that for 6300 radiation, the numbers stay pretty much constant, between 30 to 50 eV. This is now for electrons. And the numbers are also quite close for 5577. But for 3914, there is a fairly rapid increase in the number of photons produced per unit electron flux. Now, if we take a flux of some 2 to the 8th per centimeter squared second of these electrons, of 40 eV energy, these would produce 224 Rayleighs of 6300, 20 Rayleighs of 5577, and 3 Rayleighs of 3914. So that a soft flux of this character could produce some of the observed enhancements of 5577. But if you go to too high an energy, say 50 eV, then the amount of 3914 and the ionization that's produced would be too large to be compatible with observations. Now, as far as the protons are concerned, a flux of low-energy protons would, to produce any observable 5577, would also cause quite a bit of ionization and therefore 3914 radiation. And protons can only enhance the electron temperature by ionizing and generating these low-energy electrons. And of course, the high electron temperatures are one of the characteristics associated with SAR arcs. So there's no reason to suppose that low-energy protons play a role as far as the SAR arc mechanism is concerned. It's the high-energy protons in the ring current that interchange energy with the ambient plasma through these ion cyclotron waves that play the major role. If they were precipitated directly, then they would just produce an ordinary aurora. Thank you.
I'd like to pose a problem for the ion cyclotron. If I could use the board, please.
You can erase what's there. Go ahead.
A couple of years ago at an AGU meeting, Finlay and I reported electron temperature measurements and electron density measurements at 1,000 kilometres in a latitude profile, like this. The electron density at low latitudes, here's low latitudes, the equator is there, and here's the pole up here. And this would be the trough here, and this would be the auroral zone. Auroral zone there and the trough there. So the NE, the electron density went like that. The electron temperature went like this. Now, the SAR arc, as such, was observed from the ground only in a region like that. Now, the point is this, that it is this region that is normally associated with the plasma pores, whereas we're talking about a belt here of elevated electron temperatures, which is several L values wide. This might be, say, L equals 3, and this could be L equals 5, a couple of L values. Now, the point is this, that I don't think we should hinge our discussion on the SAR Arc. At the time that the theory, some first theories on this were produced, the only evidence on the electron temperature was in fact the 6300 emission from the atmosphere. So the energetically important parameter is TE. So the fact is that there is heat flux coming into the atmosphere over this very wide L value range. And even though SAR Arc is observed from the ground at this point, the energy going in here is not that much different from the energy going here, as you could see from Fred Rees' second slide. So we need an energy source, not just over a narrow region of a SAR Arc, which is normally only about 500 kilometres, but we need an energy source to span about 2,000 kilometres. So this would take us then to an energy source that is maybe overlapping the plasma sphere at one part, but is deep in space beyond the plasma sphere. And I would like to suggest that simple Coulomb collisions might still be a good candidate for the exchange of energy between protons and background magnetospheric electrons for this purpose.
I don't think there is that serious a problem here, because one of the characteristic features of SAR arcs is that they're always, or almost always, I think, associated with aurora to the north, or poleward, I should say. So that the high electron temperature here could well be associated with soft particle precipitation. You don't know whether this region here is a pure 6300 or whether it's an auroral kind of emission spectrum.
Do you mind?
Go ahead.
Oh, sorry.
That's what we're here for, discussion.
If I could respond to that, Finlay, previous to this, had done a study of these fluctuations here. There's a characteristic difference. There are two broad regions which, with this particular data, distinguish one from the other. This region is characterized by high TE and low NE. That is physically one region. Over here, he has identified these features with auroras, the active aurora. And they are a different kind where high TE is associated generally with high NE as well. And he has identified that from photographs. And so that as far as this data is concerned, just by looking at it, there are two distinct types. And there's no reason, a priori, to say that this region is different from that region, but we can say that this region is different from this one.
But surely this intermediate region, because the ionospheric densities are so low, you wouldn't need as much energy input as you would in the region associated with the plasma pores or presumably with the auroral zone itself.
Also, it's a very non-linear situation here. If this temperature here is at, say, 4,000 and this is at 6,000, that makes a significant difference in the production of the SAR Arc.
That region where N sub E is low, if that were taken in a recovery phase, that's where the ring current would be stable and there'd be no precipitation of the ring current particles from 1 to 500 kilovolts. And it may very well be that whether or not you get a SAR arc, if the ring currents are responsible, will be dependent on how steep the gradient region is on the outer edge of the plasma pause, because if it's a very shallow gradient, then the energy deposition will be spread over a wide latitude band at low altitudes. But if the gradient is very steep, then the entire ring current energy spectrum will go into an unstable mode over a very narrow latitude band over the ionosphere, and your specific energy deposition will be much greater in that local region.
I've looked recently at some 70 SAR arcs and tried to make correspondences of these SAR arcs with the plasma pause. And people have spoken of the difficulty in getting clear skies and all these things at the same time. A satellite is so that you can get spatial and temporal coincidence. And I find that if you call this the plasma pause, that the SAR arc is inside the plasma pause by 0 to 1/2 an L value on those cases where you have perfect spatial and temporal coincidence. I find also that on every occasion, and watch the way I state this, that there is a hydrogen arc about 1 L value northward of a SAR arc. There is a hydrogen arc. Every case I can see this, I see a SAR arc at the same time. So now there are times when I can see a SAR arc, when for clouds or something I can't see the H arc. But as far as I know, these two features are completely linked. An H arc about 1.5 L values north of the SAR arc. And now recently, and something that's not yet reported, in this area that Keith was talking about from here to here, I'm quite convinced that there's a very diffuse aurora, fainter than what Cliff Anger has been reporting as the diffuse aurora, which is essentially a permanent feature, particularly in the red, which underlies this whole region and increases roughly exponentially to the north on all cases when the plasma pause is well formed down around L equals 3. Those are the general characteristics of looking at about 5 years of data on which a SAR arc occurs about 1 out of every 10 nights.
Dick, when you see these H arcs, are they associated with substorms, or I know they come and go, the H arcs.
In the recovery.
Yeah, but are they associated with substorms during the recovery?
Oh yes, with a very interesting lag. If I look at the, the question was whether the H arcs are associated with substorms, and the answer is yes. If I look at the magnetometer trace, and I see what looks like an impulse, a decrease in the horizontal component, with a 45-minute time lag, for some reason or other, the brightness of the H arc comes up, and that's consistent. I've seen that time after time, and I don't know what the 45-minute time lag means.
Is that independent of local time?
I haven't seen enough cases to say that. I'd say 3 or 4 cases, and they were around pre-midnight.
If you're going to do simultaneous satellite observations at equatorial altitudes to try to correlate with both SAR arcs and the hydrogen aurora, you have to remember that 1.5 separation in L value at low altitudes during recovery phase can very easily be a 3 Earth radius separation at the equatorial region simply because of field line expansion. And that would fit in very well with the fact that there is a large region of very stable ring current trapping just outside the plasma pause region.
Of course, hydrogen arcs do occur even in the absence of SAR arcs, just auroral hydrogen arcs. Except at this time, they may move quite away.
One more comment.
Look, I'm sorry to labour this point, but I think it's tremendously important. I think we should forget about the red line and think in terms only of TE. If you like, in this region there might only be a half a photon per second coming out, but it's still a SAR arc. Energetically, the important parameter is TE, and we've got to think of this whole region as SAR arc in brackets.
Well, that certainly is true, because you can only distinguish a SAR arc above a background.
A very brief comment in some respects supporting Keith. I don't agree with him in all the details here, but I looked at 4 consecutive nights of data from August 6. On 2 of them there were SAR arcs, and 2 of them there weren't. And as far as the electron temperature looked, as a function of latitude, they looked very, very similar. So clearly all 4 nights there were heat coming in. It was fairly sharply peaked. It dropped down after here was the trough, it went up and it dropped down. The point is that the electron temperature is an indication of what the energy coming in. The emission, the SAR arc, is a very nonlinear feature. So, just a little wiggle here in the temperature will make all the difference. You'll see a SAR arc or you won't see a SAR arc. So I agree with you that the temperature is the thing that we ought to look at.